Welcome back to our course, Networks and Distributed Systems, based on the textbook by Jim Couros and Keith Ross, Computer Networking, a Top-Down Approach. We are in the process of discussing wireless and mobile networks. Let's pick up where we left off. Having discussed the pieces of a wireless network, we should note that these pieces can be combined in different ways to form different types of wireless networks. At the highest level, we can classify wireless networks according to two criteria. First, whether a packet in a wireless network crosses exactly one wireless hop or multiple wireless hops. And secondly, whether there is infrastructure such as a base station in the network. Let's look at a couple of these different ideas. In a single hop, infrastructure-based classifications, the networks have a base station that is connected to a larger wired network, like the internet. Furthermore, all the communication is between the base station and the wireless host over a single wireless hop. These are like the 802.11 networks you use in the classroom or cafe or library, and the 3G cellular networks. The next combination is the single hop infrastructureless networks that have no base station that is connected to a wireless network. However, as we will see, one of these nodes in this single hop network may coordinate the transmissions of the other nodes. Bluetooth networks and 802.11 networks in ad hoc mode are single hop infrastructureless networks. Another combination, the multi-hop infrastructure-based networks, where a base station is present that is wired to the larger network. However, some wireless nodes may have to relay their communication through other wireless nodes in order to communicate via the base station. Some wireless sensor networks and so-called wireless mesh networks fall into this category. Finally, the multi-hop infrastructureless network, where there is no base station, and nodes may have to relay messages among several other nodes in order to reach the destination. Nodes may also be mobile, with connectivity changing among nodes, a class of networks known as mobile ad hoc networks. If the mobile nodes are vehicles, the network is a vehicular ad hoc network. As you can imagine, the development of protocols for such networks is challenging and is the subject of much ongoing research. In this module, we'll mostly confine ourselves to infrastructure-based single-hop networks. Many technical challenges arise in wireless and mobile networks. We'll start by considering the individual wireless link. Consider a simple wired network, like a home network, with a wired Ethernet switch interconnecting the hosts. If we replace the wired Ethernet with a wireless 802.11 network, a wireless network interface would replace the host wired Ethernet interface, and an access point would replace the Ethernet switch. Virtually no changes would be needed at the network layer or above. So to evaluate such a change, the area to consider is the link layer. We can find several important differences between a wired link and a wireless link. First, there is a decreasing signal strength. Electromagnetic radiation attenuates as it passes through matter. That is, a radio signal passing through a wall. Even in free space, the signal will disperse, resulting in a decreased signal strength, sometimes referred to as a path loss, as the distance between the sender and the receiver increases. Secondly, there can be interference from other sources. Radio sources transmitting in the same frequency band will interfere with each other. For example, 2.4 GHz wireless phones and the 802.11b wireless LANs transmit in the same frequency band. Therefore, the 802.11b wireless LAN user talking on a 2.4 GHz wireless phone can expect that neither the network nor the phone will perform particularly well. In addition to interference from transmitting sources, electromagnetic noise within the environment, like a motor or something nearby, there can also be multipath propagation. Multipath propagation occurs when portions of the electromagnetic wave reflect off objects and the ground, taking paths of different lengths between a sender and a receiver. This results in the blurring of the received signal at the receiver. Moving objects between sender and receiver can cause multipath propagations to change over time. All this suggests that bit errors will be more common in wireless links than in wired links. For this reason, wireless link protocols employ not only powerful CRC error detection codes, but also link-level reliable data transfer protocols that retransmit corrupted frames. Having considered the impairments that can occur in a wireless channel, look at the host receiving the wireless signal. This host receives the electromagnetic signal that is a combination of a degraded form of the original signal transmitted by the sender and background noise in the environment. This signal degradation is due to the attenuation and multipath propagation effects that we just discussed, among other things. The signal-to-noise ratio is a relative measure of the strength of the received signal and this noise. For our purposes, we only need to know that a larger signal-to-noise ratio makes it easier for the receiver to extract the transmitted signal from the background noise. Figure 6.3, as you see here, shows the bit error rate, the probability that a transmitted bit is received in error at the receiver, versus the signal-to-noise ratio for 3 different modulation techniques for encoding information for transmission on an idealized wireless channel. Figure 6.3 illustrates several physical layer characteristics that are important to understanding higher-level wireless communication protocols. For example, for a given modulation scheme, the higher the signal-to-noise ratio, the lower the bit error rate. Since the sender can increase the signal-to-noise ratio by increasing its transmission power, the sender can then decrease the probability that a frame is received in error by also increasing its transmission power. There is arguably little practical gain in increasing the power beyond a certain threshold. There are also disadvantages associated with increasing the transmission power. More energy must be expanded by the sender, which is an important concern for battery-powered mobile users. And the sender's transmissions are more likely to interfere with the transmissions of some other sender. Another issue is that for a given signal-to-noise ratio, a modulation technique with a higher bit transmission rate will have a higher bit error rate. Dynamic selection of the physical layer modulation technique can be used to adapt the modulation technique to channel conditions. The signal-to-noise ratio and the bit error rate may change as a result of mobility or due to changes in the environment. Adaptive modulation and coding are used in cellular systems and in the 802.11 Wi-Fi and the 3G cellular data networks. This allows, for example, the selection of a modulation technique that provides the highest transmission rate possible, subject to a constraint on the bit error rate for a given channel characteristic. A higher and time-varying bit error rate is not the only difference between a wired and a wireless link. Remember that in the case of a wired broadcast link, all nodes receive the transmissions from all other nodes. In the case of wireless links, the situation's not that simple. As you can see here in figure 6.4, suppose that station A is transmitting to station B and that station C is transmitting to station B. With the so-called hidden terminal problem, physical obstructions in the environment, for example a mountain, may prevent A and C from hearing each other's transmissions, even though A and C's transmissions are indeed interfering at destination B. This is shown on the left-hand side of figure 6.4. A second scenario that results in undetectable collisions at the receiver results from the fading of a signal's strength as it propagates through the wireless medium. The right side of figure 6.4 illustrates the case where A and C are placed such that their signals are not strong enough to detect each other's transmissions, yet their signals are strong enough to interfere with each other at station B. The hidden terminal problem and the fading make multiple access in a wireless network considerably more complex than in a wired network. Well, that concludes this lesson. Go back and check your notes and update your study guide, and we'll continue later.